This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome to this exploration of the fascinating world of semi-Dirac fermions in topological metals. We'll be delving into the quantum realm, but don't worry, we'll explain these complex concepts in easy-to-understand language, making this journey accessible to everyone. Topological metals aren't your typical metals. They possess a unique electronic structure that gives rise to some truly mind-bending properties. Imagine electrons behaving differently depending on which direction they're moving, almost like a car that's heavier going uphill than downhill. These unusual behaviors are a consequence of the material's topology, a concept that describes the overall shape and connectivity of the electron's energy landscape. We'll be exploring the strange world of quasi-particles, which represent the collective behavior of electrons within a material. One particularly intriguing quasi-particle is the semi-Dirac fermion, which exhibits this direction-dependent behavior. We'll discover how these semi-Dirac fermions emerge in certain topological metals, specifically at the intersection of nodal lines, which are like highways in an abstract space called momentum space. Our journey will take us through the concepts of quantum geometry and the Barry phase, which describes the memory electrons acquire as they navigate their quantum landscape. We'll see how these concepts are crucial for understanding the topological properties of materials and how they influence the behavior of semi-Dirac fermions. We'll also explore the experimental techniques used to probe these hidden quantum phenomena, particularly magneto-optical spectroscopy. This technique, which involves shining light on a material in the presence of a magnetic field, allows us to decipher the material's electronic structure and confirm the existence of these elusive quasi-particles. Furthermore, we'll delve into the intriguing properties of nodal line metals, the materials that host these semi-Dirac fermions. We'll explore their unique electronic dispersion, the relationship between an electron's energy and momentum, and how it leads to unusual transport phenomena. We'll also discuss how the crossing of nodal lines creates hotspots for exotic quasi-particles to emerge. We'll then dive into the theoretical underpinnings of these materials, exploring how scientists use powerful computer simulations to predict the existence of semi-Dirac fermions and guide the discovery of new materials with tailored properties. We'll see how these theoretical predictions are confirmed by experiments, leading to a deeper understanding of the quantum world. Our exploration will also cover the unique signatures of semi-Dirac fermions, particularly the unusual scaling of Landau levels in a magnetic field and the quantum oscillations that arise from these quantized energy levels. These signatures provide crucial evidence for the existence of these exotic particles and offer valuable insights into their behavior. The anomalous Hall effect, a phenomenon where a voltage arises perpendicular to the current even without an external magnetic field, will also be a key topic. We'll see how semi-Dirac materials enhance this effect and explore its potential applications in spintronics, a field that aims to use the spin of electrons for information processing. Finally, we'll touch on the fascinating interplay between topological phase transitions and superconductivity. We'll explore how changes in external conditions or material composition can trigger dramatic shifts in the electronic structure, leading to the emergence of new quantum states and even the possibility of superconductivity. By the end of this exploration, you'll have a deeper understanding of the fascinating world of semi-Dirac fermions, their unique properties, and their potential to revolutionize future technologies. Get ready to embark on a quantum adventure. Chapter 1. Topological metals, a new frontier in materials science. Today, we're venturing into the quantum realm to explore a new class of materials that are rewriting the rules of conductivity, topological metals. These aren't your garden variety metals like the copper in your wiring or the steel in your car. Topological metals possess an unusual electronic structure, a consequence of their unique atomic arrangement, that gives rise to some truly mind-bending properties, placing them at the forefront of quantum materials research. Now, to understand what makes these materials so special, we need to delve into the world of quasi-particles. Imagine a bustling city street. Instead of tracking every single car, you might describe the traffic flow as a whole. Quasi-particles are similar. They represent the collective behavior of electrons within a material. In topological metals, these quasi-particles can take on surprising forms, like the semi-Dirac fermion, which acts as if it has different masses depending on which way it's moving. A bit like a car that's heavier going uphill than downhill. One of the key features of topological metals is the presence of what are called nodal lines. These aren't physical lines you can draw on the material. Instead, they exist in an abstract space called momentum space, which describes the possible momenta of electrons within the material. Think of it like a map of a subway system. The lines represent the different routes available. Nodal lines are similar. They map out the allowed paths for electrons in momentum space. And just like intersecting subway lines create a central transfer hub, when nodal lines cross, they can give rise to unique quasi-particles at these intersection points. So how do we even know these nodal lines and quasi-particles exist if we can't see them? We use a powerful technique called magneto-optical spectroscopy. Imagine shining a beam of white light through a prism. The prism separates the white light into its different colors, revealing its hidden composition. Magneto-optical spectroscopy does something similar. By shining light on a material in the presence of a magnetic field, and then meticulously analyzing how the light is absorbed or reflected, we can decipher the material's hidden electronic structure and deduce the presence of nodal lines, semi-Dirac fermions, and other exotic phenomena. A prime example of this is the discovery of semi-Dirac fermions in the topological metal zirconium silicide, ZrSis. Researchers using magneto-optical spectroscopy observed a peculiar behavior in the material's energy levels when placed in a magnetic field. These energy levels, known as Landau levels, exhibited a distinct B-2/3 scaling, meaning their spacing changed with the magnetic field strength raised to the power of 2/3. This unique scaling is a defining characteristic of semi-Dirac fermions, providing the first experimental confirmation of these elusive quasi-particles. The unusual electronic structure of topological metals also leads to other exciting phenomena, like the anomalous Hall effect. Imagine applying a current through a wire. Typically, you'd need a magnetic field to deflect the electrons and generate a voltage perpendicular to the current. But in topological metals, this perpendicular voltage can arise even without an external magnetic field. This is the anomalous Hall effect, a purely quantum mechanical phenomenon stemming from something called the Berry phase, which describes the geometric properties of electron wave functions. This effect has huge implications for spintronics, a field that aims to use the spin of electrons, not just their charge, to process information. The potential of topological metals extends far beyond fundamental physics. Their high electron mobility and unique transport properties make them incredibly promising for a wide range of future technologies. Think of transistors that are not only faster but also far more energy efficient than the silicon transistors powering our current electronics. Topological metals could also revolutionize data storage, leading to hard drives with capacities that dwarf today's technology. Imagine storing entire libraries on a device the size of your fingernail. The field of topological materials is still in its early stages, but the discoveries made so far are truly groundbreaking. As we continue to probe these materials, we can anticipate even more surprising revelations and advancements in the years to come. Chapter 2. Semi-Dirac fermions, unique quasiparticles with anisotropic dispersion. Let's dive into the fascinating world of semi-Dirac fermions, some of the most peculiar and intriguing quasiparticles in condensed matter physics. What makes them so special is their unique property called anisotropic dispersion. Now, before we get into what anisotropic dispersion is, let's talk about what dispersion means in physics. Imagine you're throwing a ball. The harder you throw it, the faster it goes, right? In physics, this relationship between how fast something moves, its velocity or momentum, and its energy is what we call dispersion. For most particles, like electrons roaming freely in space, if you double the momentum, you quadruple the energy. This is what we call quadratic dispersion, and it's the typical behavior of massive particles. Think of it like pushing a shopping cart. The harder you push, more momentum, the faster it accelerates, and the energy increases much more quickly. But light is different. Light particles, called photons, are massless. They always travel at the speed of light, and their energy is directly proportional to their momentum. Double the momentum, double the energy. This is called linear dispersion. Think of it like stretching a rubber band. The more you pull, more momentum, the more energy it stores, in a direct, linear relationship. Now, imagine a particle that combines both of these behaviors. That's a semi-Dirac fermion. In one direction, it behaves like a massless photon, exhibiting linear dispersion. But in the perpendicular direction, it acts like a massive electron, showing quadratic dispersion. This direction-dependent behavior is what we mean by anisotropic dispersion. It's like a strange combination of a rubber band and a shopping cart, all rolled into one quasi-particle. This anisotropic nature has some really interesting consequences for how semi-Dirac fermions behave. Let's talk about quantum tunneling, a phenomenon where a particle can pass through a barrier even if it doesn't have enough energy to overcome it classically. For semi-Dirac fermions, the probability of tunneling depends on the direction of the barrier. If the barrier is aligned with the massless direction, the semi-Dirac fermion tunnels easily, almost as if the barrier isn't there. But if the barrier is aligned with the massive direction, tunneling is much harder, like it is for regular electrons. This directional dependence could be exploited to create novel switching devices where the tunneling behavior is controlled by simply changing the orientation of the barrier. Another fascinating effect is related to Landau levels. When you apply a magnetic field to a material, charged particles move in circular orbits, and their energy levels become quantized into what we call Landau levels. These are discrete energy values that the particles can occupy, like rungs on a ladder. For semi-Dirac fermions, the spacing between these Landau levels scales differently with the magnetic field compared to ordinary electrons. This unique scaling, a direct consequence of the anisotropic dispersion, serves as a fingerprint for identifying semi-Dirac fermions in experiments. So, where do we find these exotic quasi-particles? They've been predicted to exist in various theoretical models and materials. For instance, if you imagine a graphene-like structure but modify the hopping strength of electrons between atoms, you can create a semi-Dirac point. This type of behavior has been theoretically explored in materials like vanadium dioxide, VO2, thin films embedded in titanium dioxide, TO2. Semi-Dirac fermions have also been observed at the crossing points of nodal lines in certain materials. Nodal lines are lines in momentum space where the energy bands touch. When these lines cross, they can create semi-Dirac points. This has been studied in materials like zirconium silicide sulfide, ZrSiS, barium nickel sulfide, BaNis2, and platinum ditelluride, PTTE2. These materials, known as semi-Dirac semimetals, are also intriguing because their electronic properties can be tuned by external perturbations. Applying different types of strain, like stretching the material in one direction, uniaxial strain, or in two directions, biaxial strain, can modify the electronic structure. This can cause the semi-Dirac semimetal to transition to other exotic phases, like Weyl semimetals or topological insulators. The ability to control these transitions with strain opens up possibilities for creating materials with switchable topological properties, potentially leading to advancements in future electronic devices. Chapter 3. Quantum Geometry and the Barry Phase. Unveiling the Hidden Topology. Welcome back to our exploration of the fascinating world of semi-Dirac fermions. In this chapter, we're going to dive into a concept that sounds like it belongs in a science fiction novel, quantum geometry. But I assure you, this is real, cutting-edge science, and it's absolutely essential for understanding the strange and wonderful properties of semi-Dirac fermions. Imagine the electrons in a material not just as tiny particles whizzing around, but as quantum travelers navigating a complex, invisible landscape. This landscape is the material's energy band structure, a map of the allowed energy levels for the electrons. Now, in the quantum world, things aren't always as they seem. Electrons, as they journey through this energy landscape, can pick up a kind of memory of their travels, even if they end up back where they started. This memory is called the Barry phase, and it's a fundamental concept in quantum geometry. Think of it like this. Imagine an ant walking around a curved surface like an orange. Even if the ant walks in a closed loop and returns to its starting point, its orientation has changed slightly. It's facing a slightly different direction than it was at the beginning of its journey. The Berry phase is analogous to this change in orientation. It's a subtle shift in the electron's quantum state that occurs when it travels along a closed loop in its momentum space, which is like the ant's orange, but instead of physical space, it represents the electron's momentum. Now, you might be wondering, what does this have to do with semi-Dirac fermions? Well, these unique quasi-particles reside in materials with special topologies. Topology refers to the overall shape and connectivity of the electron's energy landscape. A donut, for instance, has a different topology than a sphere because it has a hole. In topological materials, the connectivity of these energy bands plays a crucial role in determining the material's properties. The Berry phase acts like a sensitive compass, revealing the hidden topological features of this energy landscape. It's a powerful tool for probing the quantum geometry of the material, uncovering how the shape of electron paths influences their behavior. And in materials like Xerxes, where semi-Dirac fermions emerge, this becomes particularly intriguing. Xerxes, as we discussed in a previous chapter, is a nodal line metal. Nodal lines are like highways in momentum space where the electron's energy bands cross. Imagine these highways intersecting, creating a complex network. These intersections are hotspots of interesting topological activity, and semi-Dirac fermions often pop up near these crossing points. The Berry phase, in this case, becomes a sensitive probe of the topology around these nodal line crossings. A related concept, and equally important, is the Berry curvature. Imagine a vector field, like the arrows on a weather map showing wind direction, swirling around these nodal line crossings in momentum space. This swirling represents the Berry curvature, and its strength tells us how much the electron's quantum state changes as it navigates through this region. The Berry phase, then, is the total amount of swirling the electron experiences along its closed loop. It's like the ant on the orange experiencing different amounts of curvature depending on its path. Now, how do we actually measure this hidden topology and Berry phase? That's where magneto-optical spectroscopy comes in. This technique involves shining light on a material in the presence of a magnetic field. When light interacts with a material, it can excite electrons to higher energy levels. In semi-Dirac systems, the spacing of these energy levels is influenced by both the magnetic field and the Berry phase. Think of it like shining a flashlight onto a hidden landscape. The shadows and highlights reveal the contours of the terrain. Similarly, by analyzing the spectrum of light absorbed or reflected by the material, researchers can extract information about the underlying quantum geometry. They can map out the swirling Berry curvature and determine the Berry phase. A research paper by Xiao et al., published in Physical Review X, demonstrates precisely this, using magneto-optical spectroscopy to unveil the unique B-2/3 scaling of Landau levels in Xerxes, a direct consequence of semi-Dirac fermions and the underlying quantum geometry. The implications of quantum geometry and the Berry phase extend far beyond just understanding fundamental physics. They open doors to exciting new technologies. For example, materials with large Berry curvature, lots of swirling, can exhibit enhanced thermoelectric properties. Thermoelectric materials can convert heat into electricity or vice versa. A large Berry curvature effectively steers the electrons, improving the efficiency of this conversion process. This could lead to more efficient waste heat recovery systems, turning the heat from your car's engine, for instance, into usable electricity. Or it could lead to more efficient refrigeration, cooling your electronics without noisy fans. Furthermore, the electron's spin, which is like its intrinsic angular momentum, is also coupled to the Berry phase. This coupling is like a hidden connection between the electron's motion and its spin. This connection can be exploited in the field of spintronics, which aims to use the electron's spin, not just its charge, to carry and process information. Imagine a spin transistor, analogous to the transistors in your computer, but controlling the flow of spin instead of charge. Semi-Dirac materials, with their unique spin-Berry phase coupling, could be potential building blocks for such spintronic devices, leading to faster, more energy-efficient electronics. Research on materials like those discussed by Mohanta et al. In Physical Review B, exploring semi-Dirac and Weyl fermions in transition metal oxides, lays the groundwork for understanding and harnessing this spin-Barry phase coupling for future spintronic applications. The study of quantum geometry in semi-Dirac systems is still a relatively new field, but it's brimming with potential. As researchers continue to probe the topological landscapes of these materials, we can expect even more surprising discoveries and technological breakthroughs. We're not just mapping out the quantum world, we're learning how to harness its unique properties for the technologies of tomorrow. By understanding the intricate dance of electrons in the topological landscape of semi-Dirac materials, we are pushing the boundaries of both scientific knowledge and technological innovation. Chapter 4. Nodal line metals and their intriguing properties. So, we've talked about some pretty wild stuff in the quantum world, but hold on tight, because we're about to dive into a whole new level of weirdness with nodal line metals. Imagine a metal, but not the kind you'd find in your kitchen utensils. These metals have a completely different electronic structure, a unique arrangement of how their electrons are organized. Instead of the usual energy bands crossing at specific points, these materials have bands that touch along lines, like intricate, interwoven threads. We call these lines nodal lines, and they're like superhighways for electrons, allowing them to zip around with incredible freedom. Now, this isn't just some abstract concept. This unique structure gives nodal line metals some truly mind-bending properties. One of the most intriguing is something called anisotropic dispersion. Okay, bear with me, I know it sounds technical, but it's actually a pretty simple idea. Imagine you're throwing a ball. It follows a nice, predictable curve, right? That's like the typical relationship between an electron's energy and its momentum in most materials. But in nodal line metals, things get a little funky. Near these nodal lines, the relationship isn't always so predictable. It's like throwing a ball that sometimes curves like normal, but other times, it just shoots off in a straight line. This is because the dispersion, that relationship between energy and momentum, is anisotropic, meaning it depends on the direction the electron is traveling. Think of it like this: the nodal line is our electron highway. If the electron is traveling along the highway, it's in the fast lane, moving at a constant speed, almost like it's massless. But if it tries to veer off the highway, it suddenly feels the effects of its mass, and its speed starts to change with its momentum, just like that ball curving back down to Earth. This anisotropic dispersion, this directional dependence of electron movement, is a defining characteristic of nodal line metals, and it has some pretty significant consequences for how these materials conduct electricity and heat. Take zirconium silicon sulfide, or ZIRSIS for short. This material is like the poster child for nodal line metals, a perfect example of how these electron highways can create some unusual behavior. In ZIRSIS, the dispersion near the nodal lines is linear in one direction, meaning electrons zip along at a constant speed, and quadratic in the perpendicular direction, meaning they behave like more typical electrons. It's like a city with a super fast subway system. If you're on the subway, you're zipping along quickly, but if you're walking on the streets perpendicular to the subway line, your speed varies depending on how much effort you put in. This difference in electron behavior leads to some interesting transport phenomena, affecting how ZIRSIS responds to electric fields and temperature gradients. But things get even wilder in ZIRSIS. These nodal lines, these electron highways, aren't just isolated roads. They can actually cross each other, forming intricate networks in momentum space. Imagine a complex highway system with overpasses and interchanges. That's what's happening inside ZIRSIS. These crossing points are like bustling intersections where different types of electronic traffic can meet and interact. And at these intersections, something really special can happen. Exotic quasi-particles can emerge. Now, quasi-particle sounds like something out of a science fiction movie, but it's just a fancy way of describing how a bunch of interacting particles can behave like a single, independent particle. Think of it like a flock of birds. Individually, they're separate entities, but when they fly together in formation, they almost seem like one giant bird. In nodal line metals, these crossing points can host some particularly exotic quasi-particles, like semi-Dirac fermions. Semi-Dirac fermions are like hybrid particles, combining aspects of both massless and massive particles. Remember our highway analogy? Semi-Dirac fermions are like vehicles that can switch between the fast lane and the regular streets. In one direction, they zip along the nodal line at a constant speed, like they're massless. But in the perpendicular direction, they feel the effects of their mass, and their speed changes with their momentum. This hybrid nature gives them unique properties that are different from both ordinary electrons and the truly massless Dirac fermions found in materials like graphene. Xerces and its semi-Dirac fermions are just the tip of the iceberg. Nodal-lined semimetals can appear in a variety of materials, each with its own unique characteristics. For instance, certain transition metal oxides can host three-dimensional semi-Dirac fermions, taking the concept beyond the two-dimensional world of Xerces. These materials often have specific crystal symmetries that protect the existence of these quasi-particles, ensuring they aren't easily disrupted. And under the right conditions, like breaking time reversal symmetry, these semi-Dirac fermions can even transform into another type of exotic quasi-particle called whale points. Think of whale points as even more elusive and exotic particles, with unique properties that could revolutionize electronics and computing. Another exciting avenue for creating semi-Dirac points is through heterostructures. Imagine stacking different materials together like layers of a cake. That's a heterostructure. By carefully choosing the materials and how they're layered, we can engineer robust semi-Dirac points. Robust, in this context, means these quasi-particles are more stable and less susceptible to external disturbances. It's like building a sturdier highway that can withstand heavy traffic and harsh weather. A prime example of this is a heterostructure combining a superconducting layer of strontium-iridium oxide, Sr2IRO4, with a metallic layer containing what are called T2 grams electrons. This combination creates a stable environment for semi-Dirac points to exist without the need for precise fine-tuning. It's like building our electron highway in a perfect location, where the terrain and climate are just right for smooth, uninterrupted flow. These heterostructures also have the potential for something called unconventional topological phase transitions. Imagine a highway suddenly reconfiguring itself, changing the routes and connections. That's a topological phase transition. These transitions can lead to dramatic changes in the material's properties, opening up possibilities for new functionalities and devices. Now, how do we actually study these elusive quasi-particles and their behavior? Well, scientists have developed some pretty ingenious experimental techniques. One of the most powerful is magneto-optical spectroscopy. Imagine shining a light on our electron highway and then turning on a strong magnet. That's the basic idea behind magneto-optical spectroscopy. By studying how the light interacts with the material in the presence of the magnetic field, we can uncover some telltale signs of these exotic quasi-particles. Specifically, we can observe the scaling of Landau levels, which are like the different lanes on our electron highway. Each lane corresponds to a different energy level that electrons can occupy, and the spacing between these lanes can reveal the unique signature of semi-Dirac fermions. It's like analyzing the traffic patterns on our highway to understand the behavior of the vehicles traveling on it. This technique allows us to delve into the topological properties of nodal-line metals, revealing their intricate connection to the quantum world. We'll dive deeper into these experimental techniques in a later chapter, but for now, just know that they provide crucial insights into the unique physics of these materials. Beyond Xerces, H-boron, and transition metal oxides, the world of nodal-line semimetals is vast and largely unexplored. Another theoretical example is H-boron, a hexagonal arrangement of boron atoms, which has been predicted to be a nodal-line metal with exceptional stability and mechanical properties. What's even more exciting is the sheer variety of exotic fermions it's predicted to host, including not just semi-Dirac fermions, but also triple-point fermions, which are like three-way intersections in our highway analogy, and even nodal surface fermions, expanding the concept of electron highways to entire surfaces. H-boron is like a futuristic city with a multi-layered transportation network, offering a playground for exploring a wide range of novel physical phenomena. The story of nodal-line metals is still being written. Scientists are constantly discovering new materials with these unique electronic structures, and the possibilities seem endless. From developing new types of electronic devices to understanding the fundamental nature of quantum matter, nodal-line metals offer a fascinating frontier in materials science. So, next time you pick up a metal object, Remember that there's a whole universe of hidden complexity within, and materials like nodal line metals are pushing the boundaries of what we thought was possible. Chapter 5. The Quantum Quest for Semi-Dirac Materials, a virtual laboratory for discovery. So, we've been talking about these intriguing semi-Dirac fermions, these quantum particles that seem to defy simple categorization. They're like a hybrid of the speedy electrons in graphene and the more commonplace, slower electrons we're used to. But how do we even find these elusive particles? How do we know where to look in the vast universe of materials? That's where the magic of theoretical predictions comes in, especially predictions based on what scientists call ab initio calculations. Now, ab initio is just Latin for from the beginning, and it means we're starting with the very basics. Imagine trying to understand a complex machine like a car. You could start by taking it apart, examining each piece, and figuring out how it works. Or, you could start with the blueprint, the fundamental design, and build your understanding from there. A flat initio calculations are like that blueprint for materials. Instead of relying on experiments or guesswork, these calculations use the fundamental laws of physics, specifically quantum mechanics, to predict how electrons will behave in a material. We're talking about the quantum world here, where things get really weird and counterintuitive. But with the help of powerful computers, we can simulate these quantum behaviors and predict the properties of materials before they even exist in the real world. It's like having a virtual laboratory where we can design and test new materials at the atomic level. This virtual laboratory is crucial in the hunt for semi-Dirac materials. It allows us to explore the complex dance of electrons in different materials and identify those with the right conditions for hosting these unique semi-Dirac fermions. Let me give you an example. There's a material called zirconium silicide sulfide, or ZIRSIS for short. Scientists already knew it was a nodal line metal. That means its electronic structure, sort of like a map of electron energies, has lines where the allowed energy levels for electrons touch. Think of these lines as open highways for electrons to zip around freely. What scientists didn't know until recently, and this is where ab initio calculations really shined, was that at certain points where these electron highways intersect, something special happens. Semi-Dirac fermions pop up. These calculations didn't just predict their existence, they also gave us a way to prove it. They predicted a unique signature, a specific way these fermions would behave in a magnetic field, that could be measured with a special technique called magneto-optical spectroscopy. And lo and behold, experiments confirmed the prediction, providing the first concrete evidence of semi-Dirac fermions in ZIRSIS. The story of ZIRSIS is a perfect example of how theory and experiment work hand in hand. But the quest for semi-Dirac materials is far from over. Scientists are using ab initio calculations to explore a vast array of materials, searching for other potential homes for these fascinating particles. One promising area is transition metal oxides. These materials are known for their diverse electronic behaviors. Some can be magnetic, others become superconductors, and some even act like topological insulators. Calculations have revealed that certain transition metal oxides with specific atomic arrangements can support three-dimensional semi-Dirac fermions. This is a big deal because most previous studies focused on two-dimensional systems like graphene. Another exciting prediction involves a hypothetical form of boron called H-boron. It has a hexagonal structure, similar to diamond. Calculations suggest this material could be a topological metal, meaning it has unique surface properties protected by its shape and arrangement of atoms, and it could potentially host a whole zoo of exotic particles, including semi-Dirac fermions. While H-boron is still a theoretical concept, it shows the incredible power of ab initio calculations to guide the creation of new materials with tailored properties. But ab initio calculations do more than just predict new materials. They also help us understand the fundamental nature of semi-Dirac fermions themselves. For example, studies have explored the role of something called spin-orbit coupling. This is the interaction between an electron's spin, think of it like a tiny internal compass, and its motion. It turns out that spin-orbit coupling can influence the formation and stability of semi-Dirac points. These calculations have also shown us how we can manipulate these points using external forces like stretching the material or applying an electric field. This deeper understanding is essential for harnessing the potential of semi-Dirac materials for future technologies. One particularly intriguing application involves creating what are called heterostructures. These are layered materials made by stacking different components on top of each other, kind of like a high-tech sandwich. Researchers are particularly interested in heterostructures that combine superconductors, materials that conduct electricity with zero resistance, with metallic systems containing specific electron orbitals called T2 electrons. Think of these orbitals as specific paths that electrons can take within an atom. Calculations predict that these heterostructures can harbor robust semi-Dirac points without the need for precise adjustments, and these points can even split into stable Dirac points under the right conditions. This opens up exciting possibilities for designing new types of topological superconductors and exploring strange and unconventional transitions between different quantum states. Let's delve a bit deeper into the world of heterostructures, as they represent a really fascinating frontier in materials science. Imagine being able to pick and choose materials with different properties and combine them like Lego bricks to create entirely new functionalities. That's the basic idea behind heterostructures. We can take a material that's a great superconductor, like strontium iridate oxide, Sr2IRO4, and combine it with another material that has interesting metallic properties, and see what emerges. The exciting thing is that these combinations often lead to unexpected and emergent properties that neither material possesses on its own. In the case of the superconducting Sr2IRO4 combined with metals containing T2 electrons, ab initio, calculations have been instrumental in predicting the emergence of these robust semi-Dirac points. They allow us to simulate how the electrons from the two different materials interact at the interface, where they meet. This interface is where the magic happens, where new physics can arise. What's even more remarkable is that these calculations predict that under certain conditions, these semi-Dirac points can further split into stable Dirac points. Now, Dirac points are like the birthplace of massless Dirac fermions, particles that behave as if they have no mass, leading to incredible speed and mobility. This transformation from semi-Dirac to Dirac points in heterostructures offers a pathway to engineer materials with highly controllable electronic properties. The ability to manipulate these Dirac and semi-Dirac points using external factors like strain or electric fields adds another layer of control. Imagine being able to tune the electronic properties of a material in real time by simply applying a little bit of pressure or an electric voltage. This level of control could revolutionize electronics, leading to faster, more efficient, and more versatile devices. The journey into the realm of semi-Dirac materials is an ongoing adventure. At flat initio, calculations are not just a theoretical tool. They're a powerful lens through which we can explore the quantum world. They provide us with the ability to predict the existence of new particles, design materials with exotic properties, and understand the fundamental principles governing the behavior of matter at the most fundamental level. As we continue to refine these computational techniques and combine them with cutting-edge experiments, who knows what other wonders of the quantum world we might uncover. Chapter 6. Landau level scaling and quantum oscillations, signatures of semi-Dirac behavior. Electrons in materials can only exist at specific energy levels, much like a person can only stand on the rungs of a ladder, not between them. When you apply a magnetic field to a material, these energy levels get reorganized into new, equally spaced levels called Landau levels. Think of it like the magnetic field transforms the ladder into a staircase with evenly spaced steps. Typically, the energy of these Landau levels increases proportionally to the strength of the magnetic field. Increasing the magnetic field is like increasing the height of each step in the staircase. However, in certain special materials called nodal line metals, things get more interesting. These metals have unique features in their electronic structure, kind of like lines connecting mountain peaks in a 3D landscape. At the points where these lines intersect, the electrons behave like a unique type of quasiparticle called semi-Dirac fermions. Semi-Dirac fermions are unusual because they act like massless particles in one direction and massive particles in the other. This dual nature leads to a peculiar behavior in their Landau levels. Instead of increasing linearly with the magnetic field, the energy of these Landau levels increases with the 2/3 power of the magnetic field. It's as if increasing the magnetic field not only makes the staircase steps taller but also compresses them in one direction. This distinct magnetic field dependence, the B-2/3 scaling, is a key characteristic of semi-Dirac fermions and confirms their existence in materials like zirconium silicide sulfide, ZrSiS. ZrSiS is a nodal line metal, and it's at the intersection of these nodal lines that the electrons exhibit this semi-Dirac behavior. One way we can observe this unique scaling is through magneto-optical spectroscopy. We shine light onto the material while a magnetic field is applied. The electrons in the material can absorb the light, but only if the light's energy exactly matches the energy difference between two Landau levels. It's like the light provides the energy for electrons to hop up the staircase, but they can only hop from one step to another, not halfway. By carefully measuring the light absorbed at different magnetic field strengths, we can determine the energies of the Landau levels and confirm their unusual scaling behavior. Essentially, we're measuring how the staircase changes as we adjust the magnetic field. These quantized Landau levels also lead to another fascinating effect: quantum oscillations. Certain material properties, such as magnetization or resistance, can oscillate as we change the magnetic field. These oscillations are a direct consequence of the Landau level quantization. It's like as we change the magnetic field, the staircase shifts, and these shifts cause the material's overall properties to oscillate. The frequency and amplitude of these oscillations are directly related to the shape of the Fermi surface, which is the boundary in momentum space separating occupied and unoccupied electron states. Imagine the Fermi surface as the shoreline of a lake in a mountain range, representing the highest energy level electrons can occupy. In semi-Dirac systems, the Fermi surface has a unique shape influenced by the nodal lines, and this shape directly affects the characteristics of the quantum oscillations. It's as though the shape of the lake, and thus the oscillations, is determined by the surrounding mountains and connecting ridges. By studying these oscillations, we can learn about the topology of the Fermi surface and, therefore, the underlying electronic structure of the semi-Dirac material. It's like analyzing the oscillations of the lake's shoreline tells us about the shape of the lake and the surrounding mountains. In materials like ZrSiS, the interplay of nodal lines, the resulting semi-Dirac behavior at their crossings, and the unique Landau level scaling provide a rich playground for exploring the fascinating world of topological materials and their potential for future technologies. Chapter 7: Magneto-optical spectroscopy, probing the electronic structure of semi-Dirac materials. Welcome back to the podcast. Grab your headphones, settle in, and prepare to explore the fascinating world of semi-Dirac materials, viewed through the lens of a powerful technique called magneto-optical spectroscopy. It's a bit of a mouthful, I know, but the insights it provides are truly remarkable. Imagine you're a detective trying to understand the inner workings of a complex clock. You might shine a light on it, examining its gears and springs. But what if you could also apply a magnetic force, observing how the delicate mechanisms respond to this external influence? That's essentially what magneto-optical spectroscopy does for materials. It combines light and magnetic fields to reveal the intricate dance of electrons within. Now, in the case of semi-Dirac materials, this technique becomes especially intriguing. These materials, as we've discussed, host unique quasiparticles called semi-Dirac fermions. These aren't your everyday electrons, they possess a peculiar duality. In one direction, they zip around freely like massless particles, akin to photons of light. But in the perpendicular direction, they behave like particles with mass, experiencing the inertia we're all familiar with. Magneto-optical spectroscopy offers a direct way to probe this unusual, anisotropic nature. One of the key revelations comes from studying what are known as Landau levels. Picture an electron in a magnetic field. It doesn't just travel in a straight line. The magnetic force causes it to curve, tracing out a circular path. These circular orbits are quantized, meaning they can only exist at specific, discrete energies. These energy steps are the Landau levels, like rungs on a ladder. For ordinary materials, the spacing between these rungs is uniform. But for semi-Dirac fermions, The latter is a bit more peculiar. The spacing between the rungs changes depending on the strength of the magnetic field, following a unique pattern, a power law related to B caret 2/3, where B represents the magnetic field strength. This distinct scaling acts as a fingerprint, a telltale sign of the semi-Dirac nature of the quasi-particles. It's like identifying a musical instrument by the specific frequencies it produces. A flute sounds different from a violin because the resonant frequencies, like Landau levels, are determined by the instrument's unique structure. But the story doesn't end with Landau levels. Magneto-optical spectroscopy also allows us to delve deeper into the electronic structure, revealing other hidden characteristics. Think of it as using different lenses on a microscope. Each lens reveals a different aspect of the specimen. In our case, we can extract information about the effective mass of the quasi-particles, how heavy they behave in the massive direction. We can also determine their velocity in the massless direction, and even detect the presence of any energy gaps in the material's electronic spectrum. These details help us paint a comprehensive picture of how these quasi-particles behave and interact. Now, let's talk about light. Semi-Dirac materials don't just respond to magnetic fields, they also interact with light in fascinating ways. This interaction is profoundly influenced by the presence of a magnetic field, giving rise to phenomena like cyclotron resonance and Faraday rotation. Imagine pushing a child on a swing. If you push randomly, the swing won't go very high. But if you time your pushes just right, matching the swing's natural frequency, the child will swing higher and higher. Cyclotron resonance is similar. When the frequency of the incident light matches the cyclotron frequency, the rate at which the electrons orbit in the magnetic field, the material absorbs the light strongly. It's like the swing absorbing the energy of your perfectly timed pushes. Faraday rotation, on the other hand, involves a change in the polarization of light. Light, as you may know, can be polarized, meaning its electric field oscillates in a specific direction. When polarized light passes through a semi-Dirac material in a magnetic field, its polarization direction rotates. This rotation, like the amount a sugar solution rotates polarized light, is directly linked to the material's electronic structure, providing yet another way to probe the properties of these fascinating quasi-particles. These magneto-optical effects aren't just scientific curiosities. They hold potential for exciting technological applications. The strong magneto-optical response of some semi-Dirac materials could be harnessed to develop new types of optical devices, magnetic sensors, or even contribute to the advancement of quantum computing. It's like discovering a new material with exceptional strength or conductivity. Such a discovery could lead to breakthroughs in various fields, from building lighter and more efficient vehicles to creating faster and more powerful electronics. Let's move on to some specific examples where magneto-optical spectroscopy has been particularly illuminating. Consider nodal line metals. These materials have special lines in their electronic structure where energy bands meet, forming nodal lines. At the points where these nodal lines intersect, unique electronic excitations can arise. Magneto-optical spectroscopy has been crucial in identifying and characterizing these excitations, often revealing the presence of semi-Dirac fermions lurking at these crossing points. It's like using a metal detector to pinpoint buried treasure. The magneto-optical response acts as the signal, revealing the hidden semi-Dirac fermions. Furthermore, magneto-optical spectroscopy has played a vital role in uncovering the topological properties of semi-Dirac materials. Topology, in this context, refers to certain geometric characteristics of the electronic wave functions. A key concept here is the Berry phase, a sort of twist that electrons acquire as they move through the material's electronic landscape. Magneto-optical measurements, especially Faraday and Kerr rotation experiments, can be used to probe this Berry phase, revealing the hidden topological features. This information is essential for understanding the unique transport properties of semi-Dirac materials and their potential applications in spintronics, a field that aims to control and manipulate electron spin for information processing. Finally, let's touch on strain engineering. Imagine squeezing or stretching a material. This seemingly simple act can profoundly alter its electronic structure. Researchers have used magneto-optical spectroscopy to study layered materials under strain, observing the emergence of semi-Dirac fermions as the material is deformed. It's like transforming graphite into diamond by applying immense pressure. The strain changes the material's atomic arrangement, and in the case of layered materials, it can induce the formation of these unique semi-Dirac states. This ability to manipulate the electronic structure through strain opens exciting possibilities for creating new quantum states and tailoring materials with specific properties. These are just a few glimpses into the power of magneto-optical spectroscopy in the exploration of semi-Dirac materials. It's a field brimming with potential, and as researchers continue to refine this technique, we can anticipate even more groundbreaking discoveries, leading to a deeper understanding of these extraordinary materials and their potential to reshape future technologies. Chapter 8. The Anomalous Hall Effect and Spintronics Applications of Semi-Dirac Systems. Let's talk about how we can harness the strange world of semi-Dirac materials to build the next generation of electronics. Specifically, we're diving into spintronics, a field that goes beyond simply using the charge of electrons and taps into their spin, their intrinsic angular momentum, like a tiny internal compass needle pointing either up or down. Imagine the possibilities if we could control both the charge and the spin, faster, smaller, and much more energy-efficient devices. Semi-Dirac materials, with their unique properties, offer a tantalizing glimpse into this future. One star of the show is the anomalous Hall effect. Now, you might remember the regular Hall effect from physics class. Apply a magnetic field across a current-carrying wire, and the electrons get deflected, creating a voltage perpendicular to both the current and the field. The anomalous Hall effect is similar, but with a twist. It happens in certain magnetic materials even without an external magnetic field. It's like the material has its own internal, microscopic magnetic field that does the deflecting. Semi-Dirac materials take this even further. Their unusual electronic structure, where electrons act like massless particles in one direction and massive particles in another, supercharges the anomalous Hall effect, making it much stronger than in conventional materials. This enhancement isn't just a scientific curiosity, it has real-world implications. Think ultra-sensitive magnetic sensors, capable of detecting minute magnetic fields, or memory devices that store information based on the direction of the anomalous Hall voltage. So, what's the secret sauce behind this amplified effect? It boils down to something called Berry curvature, a concept tied to the topology of the electronic structure. Imagine an electron navigating a complex landscape in momentum space, the abstract space representing the electron's momentum. As it travels along a closed loop, its internal compass needle, its spin, can rotate even if the electron moves straight ahead in this momentum space. This rotation is similar to the Berry phase, a geometric property acquired by the electron on its journey. Berry curvature measures how much this geometric phase changes as the electron's momentum shifts. Semi-Dirac materials, with their unique band structures, can have regions of extremely high Berry curvature. Think of it as a mountainous terrain in momentum space, with sharp peaks and valleys. These mountains of Berry curvature drastically amplify the anomalous Hall effect, leading to the enhanced effects we've discussed. For example, research has shown that in materials like Xerxes, the crossing points of nodal lines, lines in momentum space where the valence and conduction bands touch, exhibit singularities in the Berry curvature, leading to a distinct scaling of Landau levels with the magnetic field. This specific scaling behavior, observed through magneto-optical spectroscopy, is a direct consequence of the semi-Dirac nature of the electrons near these crossing points. This brings us to the topological aspect. Topology is a branch of mathematics concerned with properties that don't change under continuous deformations. It's like comparing a donut and a coffee mug. They look different, but you can morph one into the other without cutting or gluing. Similarly, the topological properties of semi-Dirac materials protect certain features of their electronic structure, making them robust against disturbances. This robustness is crucial for building reliable devices that perform consistently even under changing conditions. Now, back to spintronics. Semi-Dirac materials have another trick up their sleeve: the ability to create spin-polarized currents. This means the spins of the electrons in the current are predominantly aligned in one direction. This is achieved through a phenomenon called spin momentum locking, where the direction of the electron's spin is inherently tied to the direction of its movement. It's as if the electron's compass needle is always pointing in a specific direction relative to its motion, like a well-trained dancer perfectly coordinating their spins with their steps. This spin momentum locking acts like a filter, allowing us to select electrons with a specific spin orientation, creating a spin-polarized current. These currents are the lifeblood of spintronic devices, particularly magnetic random access memory, or MRAM. MRAM stores information using the magnetic orientation of tiny magnetic regions. Spin-polarized currents can switch the magnetization of these regions, writing and reading data. The more polarized the current, the more efficient and faster the switching. Semi-Dirac materials, with their potential for high spin polarization, could revolutionize MRAM technology. Researchers are also exploring ways to tailor the electronic properties of these materials. One approach is applying strain, mechanically stretching or compressing the material. This deformation can alter the band structure, moving the Dirac points or even triggering topological phase transitions, essentially changing the very nature of the electronic states. Imagine morphing our momentum space landscape, creating new peaks and valleys, and thus changing the electron's behavior. Another method involves creating heterostructures, sandwiches of different materials layered together. At the interface between a semi-Dirac material and another material, like a superconductor, entirely new phenomena can arise. One especially exciting prospect is the creation of Majorana fermions, particles that are their own antiparticles, a concept straight out of science fiction. These exotic particles are incredibly stable and have been proposed as building blocks for topological quantum computers, a revolutionary type of quantum computer that is far more resistant to errors than current designs. Theoretical studies, as highlighted in some research papers, have explored the feasibility of inducing topological superconductivity in Majorana fermions in heterostructures involving semi-Dirac materials like doped superconducting SR2IRO4 coupled with specific electron systems. The theoretical landscape is rich with predictions of semi-Dirac fermions in a surprisingly diverse range of materials, from transition metal oxides like VO2 embedded in TO2, to boron allotropes like hexagonal supertetrahedral boron, and even in organometallic frameworks like those containing Zn, Cd, or Hg. These predictions have fueled experimental efforts, leading to the discovery of semi-Dirac systems in real materials like Xerxes and Nite-2. These experimental observations, often involving techniques like magneto-optical spectroscopy and angle-resolved photoemission spectroscopy, provide crucial confirmation of the theoretical predictions and offer valuable insights into the unique properties of these materials. The journey of semi-Dirac materials is just beginning, but their combined anisotropic dispersion, topological protection, and potential for enhanced anomalous Hall effect and spin-polarized currents position them as a powerful platform for both fundamental physics discoveries and technological breakthroughs in spintronics. As research continues, we can expect to unlock even more of their hidden potential, paving the way for a new era of electronic devices. Chapter 9. Topological phase transitions and superconductivity, exploring the interplay. Picture a dance floor crowded with electrons, all moving to the rhythm of a material's electronic structure. Now, imagine the music changing, not just the tempo, but the entire genre. The dancers rearrange themselves, forming new patterns, and the whole scene transforms. That's the essence of a topological phase transition, a dramatic shift in a material's electronic properties. And when those dancers are semi-Dirac fermions, the choreography becomes particularly intricate and mesmerizing, especially when the new dance leads to the elegant, frictionless flow of superconductivity. These transitions aren't like flipping a light switch. They're subtle, often driven by tiny tweaks in external conditions or the material's makeup. Take, for instance, a material like zirconium silicide, Xerxes. It's a nodal line metal, meaning its electronic band structure contains special lines where energy bands meet, like intersecting highways for electrons. At the points where these nodal lines cross, something extraordinary happens. Semi-Dirac fermions emerge. These quasi-particles are like chameleons, changing their behavior depending on the direction they move. Along one axis, they glide freely like massless photons. Along the other, they trudge along like ordinary, massive electrons. This dual nature is reflected in a peculiar scaling of their Landau levels, the quantized energy levels they occupy in a magnetic field. Specifically, the energy levels scale with B caret 2/3, where B is the magnetic field strength, a telltale sign of semi-Dirac behavior, observed experimentally through magneto-optical spectroscopy. Now, let's introduce a change to our Xerces crystal, perhaps a slight strain or a subtle shift in its chemical composition. This seemingly small change can have a profound effect on the nodal lines, causing them to pull apart like stretched rubber bands. As the nodal lines separate, the crossing points vanish, and with them, the semi-Dirac fermions disappear. This separation isn't just a rearrangement. It's a fundamental shift in the material's topological properties, a topological phase transition. The connection to superconductivity comes into play when we consider the stability of these crossing nodal lines. The crossing points can represent a kind of electronic tension, an instability waiting to be resolved. The topological phase transition, triggered by strain or compositional changes, provides a way for the material to relieve this tension, settling into a new, more stable state. And in certain materials, this relaxed state can be a superconducting one. While the precise mechanisms are still being unraveled, the basic idea is that the instability associated with the crossing nodal lines and the semi-Dirac fermions can, under the right conditions, give way to the formation of Cooper pairs, the electron duos that perform the superconducting waltz. This transition isn't guaranteed. It depends on the specifics of the material and the nature of the interactions between electrons. But the possibility is tantalizing, offering a potential pathway to designing new superconducting materials by manipulating their topological properties. Heterostructures offer another intriguing playground for this interplay. Imagine a thin layer of strontium ruthenate, Sr2RuO4, a material known for its strong spin-orbit coupling, placed on top of a superconductor. Spin-orbit coupling is a relativistic effect that intertwines an electron's spin, its intrinsic angular momentum, with its motion. This layered structure, a heterostructure, isn't just a simple stack. It's a new material with emergent properties. At the interface between the Sr2RuO4 and the superconductor, something remarkable can happen. Semi-Dirac points can spontaneously arise. These points are topologically protected, meaning they're incredibly robust, like knots that are hard to untie. Now, let's add another layer to our structure, another superconductor on top of the Sr2RuO4. This triple-decker sandwich isn't just a thicker version of the original heterostructure, it's a whole new ballgame. The semi-Dirac points, once stable and singular, can now split into two distinct Dirac points. These Dirac points aren't just copies of each other. They have opposite chiralities, like mirror images. Think of chirality as handedness. Just as your left hand won't fit into a right-handed glove, these chiral Dirac points distinguish themselves by the way they interact with other particles and fields. This splitting is another example of a topological phase transition, driven by the addition of the extra superconducting layer. It offers the ability to fine-tune the material's properties, potentially leading to novel electronic devices that exploit the distinct behavior of chiral Dirac fermions. We can even induce a similar transition by introducing triplet superconductivity into the Sr2RuO4 layer. Triplet superconductivity is a special type of superconductivity where the Cooper pairs have parallel spins, unlike conventional superconductivity where they have opposite spins. This change in pairing alters the delicate balance of interactions within the material, leading to a topological phase transition and the emergence of chiral Dirac points. The specifics of the resulting phase diagram, the map of different electronic states as a function of various parameters, depend on the details of the material and the strength of the superconducting pairing. The examples of Xerces and Sr2RuO4-based heterostructures illustrate how topological phase transitions in semi-Dirac materials can be controlled and manipulated by external factors like strain, composition, or the introduction of superconductivity. These transitions aren't just abstract concepts. They represent real, measurable changes in the material's electronic structure, often accompanied by dramatic shifts in its properties, including the potential emergence of superconductivity. This interplay between topology and superconductivity is a hotbed of research, with scientists constantly pushing the boundaries of our understanding. The goal is not just to discover new materials, but to unravel the intricate dance of electrons that gives rise to these remarkable phenomena, paving the way for future technologies that exploit the quantum world. Semi-Dirac fermions, quasi-particles exhibiting both massless and massive behavior depending on the direction of motion, reside within the intriguing realm of topological materials. These materials, like nodal-aligned metals, possess unique electronic structures, with energy bands touching along lines in momentum space. At the intersection of these nodal lines, semi-Dirac fermions emerge, showcasing unusual properties like anisotropic dispersion and distinct Landau-level scaling in magnetic fields. This peculiar B-2/3 scaling, confirmed through magneto-optical spectroscopy, serves as a fingerprint for identifying these exotic particles. Quantum geometry, specifically the Berry phase and curvature, plays a crucial role in understanding these materials. The Berry phase, a quantum memory acquired by electrons as they traverse momentum space, reveals the topological features influencing semi-Dirac fermion behavior. Magneto-optical techniques, combining light and magnetic fields, provide a powerful tool to probe these hidden topological properties and the electronic structure of these materials, including cyclotron resonance and Faraday rotation. Theoretical predictions, particularly ab initio calculations, are indispensable in the quest for new semi-Dirac materials. These computations, based on fundamental quantum mechanics, guide the discovery and design of materials with tailored properties, including heterostructures, layered combinations of different materials with emergent properties at their interfaces. The anomalous Hall effect, a voltage arising perpendicular to current even without an external magnetic field, is significantly enhanced in semi-Dirac systems due to their unique band structure and high Berry curvature. This enhancement has promising implications for spintronics, a field aiming to utilize electron spin for information processing. Spin momentum locking in these materials allows for the creation of spin-polarized currents, vital for devices like magnetic random access memory (MRAM). Topological phase transitions, driven by changes in external conditions or material composition, can dramatically alter the electronic structure of semi-Dirac materials. These transitions can lead to the emergence of new quantum states, including the possibility of superconductivity, a state of zero electrical resistance. The interplay between topological properties and superconductivity is a fertile ground for research, with potential for designing novel superconducting materials. The exploration of semi-Dirac fermions is a journey into the heart of quantum phenomena, with potential to revolutionize future technologies. From novel electronic devices and magnetic sensors to advancements in quantum computing and spintronics, the possibilities are vast. What are your thoughts on the potential of semi-Dirac materials? Share your questions and insights in the comments below. Don't forget to like, subscribe, and suggest topics for future videos. The quest for knowledge is a continuous adventure, and your curiosity is the compass that guides us. Keep exploring, keep questioning, and keep learning. The wonders of the quantum world await.